guys, what's going on? My name is Professor Jennifer Hill and I run Divide and Conquer Math, which is a website and YouTube channel dedicated to helping you learn math on your terms. So this video is a part of my Study with a Math Professor series, and I always just have one of these little intros just to make sure that you know what this video is about. So my Study with a Math Professor series is a series dedicated to giving you problem sets and things to practice so that you could prepare for a test. So if you've never heard my advice on how you should study for a test, I can really summarize it as practice, practice, practice. But if you want to hear all of my advice on that, you can look in the description of this video, and I've got a link to my advice video below. So in this video, I'm not going to teach you what to do for a test. Instead, I'm going to provide you with problems and an answer key to help you kind of work through things. So the way that this video works is for the first hour, we'll study. So if you have trouble getting started, consider maybe just having this video up and you can work alongside it for an hour, and then that's an hour that you've dedicated towards studying. And I recommend that you work on the practice set for this particular video. In this video, we are focusing on difficult derivatives. Now, if you feel like maybe you need to take a step back and you want to work more on the basics, you can look in the description of this video, and I have a link to my basic problem set, and I have actually the links to all the problem sets in this particular derivative series. But I would recommend, if you're watching this, maybe work on that difficult problem set. You've got the answer key in the free download. So if you look in the description, you can find that problem set. It's a free download. It also comes with the answer key. Any problems that you don't get right or that you don't know how to do, you can also look in the description of this video, and then you will see time markers for all of the individual problems. And if there's something that you really don't know how to do, again, in the problem set, I actually have links to other videos that you can go and watch. So like I said, I don't teach you in this video, but my whole channel is dedicated to teaching you. So if you want to go back and review something, you can just look in that problem set, and I've got lots of links to kind of direct you to where else you can look. Okay, so with that being said, I'd love to hear from you guys if you are watching these or if you're using these to study. So if you can leave me a like or a comment or hit the subscribe button, that is super awesome. And otherwise, let's get started.
Hey guys, so if you're not done with the problem set, hit pause here. I'm going to start going through the solutions. So starting with the first couple of problems, what we want to do here are just find the derivatives. And so to take the derivative of this first problem, we've got to use the chain rule. And we're going to use the chain rule in a couple different ways. So the first thing that you want to do with the chain rule is you just want to recognize where are kind of all of your different functions, how are they being composed. So the outermost function is this cosine function. The next function is this square root function. And then the next one in after that is this sine squared x plus 3. Now, in taking this derivative, we have to use the chain rule again, but we'll worry about that when we get there. We've kind of got a good game plan for this. And then when we get to this derivative, we'll talk about using the chain rule again. Okay, so if I want to find f prime, so first I take the derivative of the outermost function, which would be negative sine. So the derivative of cosine is negative sine. And remember, you leave all of the other stuff intact. So this sine squared x plus 3, that's all just coming along for the ride right now. Okay, so now I want to multiply that by the next function moving in. So that would be this square root function. So that derivative is going to be 1/2. I leave the inside function intact like this. And I just take the derivative around it. So there's the derivative of that next function. Okay, so now I want to move on to the next function in, which is this one. Now, in this, we know that the derivative of 3 is just going to be 0, so really I have to worry about taking this derivative here. So notice that sine squared x, this is the same thing as sine x squared, which indicates then that we have kind of two more derivatives in this, if that makes sense. So what I want to do with this is I want to take the derivative of this outside portion here, this thing that's being squared, and then I can take the derivative of the sine function. Okay, so to take the derivative of the outermost function here, I bring down the 2. I leave the inside intact, and I subtract 1 from the exponent, so I can just leave this as sine x. And then I multiply that by the derivative of sine, which is just cosine of x. So there's all your pieces. So there's quite a bit to this. Okay. So from here, now it's really just a matter of making this look nicer. So notice as we kind of multiply everything across, one thing that I notice, the 1/2 and the 2 at least cancel out. And there's not a lot of other cancellations that we can really make here. So to finish this, I'm going to have, let's see, how about negative cosine x, sine of x, and then sine square root of sine squared x plus 3. All of that over this guy right here. So all of that over the square root of sine squared x plus 3. And so that's it. We're done. So moving on to number 2 here. So I've got g of x equals sine squared x to the 7th. So the whole thing about these squares are you want to make sure that you're thinking about them in the right way. So if I wanted to rewrite this would really be sine of x to the 7th, and then it's all of this is what's being squared, if that makes sense. So you do want to make that distinction in your mind. And we're going to use the chain rule here. And so I can see now by looking at this, my outermost function is this thing that's being squared. The next function in is this sine, and then the innermost function is this x to the 7th. So I'll color code all of that while I take the derivative. Okay, so starting with the outermost function, so I'll just use the power rule, so I'll bring that 2 down, and I leave the rest of the inside intact, like this, okay? Next, I multiply that by the derivative of the next function in, which is sine. The derivative of sine is cosine. Once again, I leave the inside function intact. And then finally, I take the derivative of the innermost function, which will be 7x to the 6th. So there's all the pieces to it. So now, if I just want to make this look nicer, so let's see, this will be 14x to the 6th. Cosine, let's do cosine x to the 7th, and then sine of x to the 7th. And you don't have to have these parentheses around these x's. I just did just to make it like clear kind of where everything is grouped, but you don't have to have them. So for number 3, we're going to be using the chain rule again. And so in this case, we have, let's see, I have my outermost function is this cube root thing, so that's the outermost. And then I move into taking this derivative here. Now, what you might notice is that I have to use the chain rule here. But what I want to do is like this chain rule is like part of taking this whole derivative here. So I'm going to hold off on worrying about what to do with the chain rule here until I get there. So let's just start setting up taking the derivative. So if I go ahead and evaluate this, so for y prime, this will be 1/3. I leave the inside function intact like this, and then I subtract 1 from the exponent. So there's kind of my outermost derivative. And now I want to multiply that by the derivative of the inside. Now, when I take this, the derivative of 2x is 2. And now I have to think about inside and outside functions with this part right here. So the outermost function here is this sine, and the innermost function is this 4x. So if I take the derivative of the sine function, that'll be cosine, and I leave the inside intact. And then I multiply that by the derivative of the inside function, which is just 4. So there's all the work that goes into that. And so now from here, we're just going to clean this up. So let's see. I can clean this up as 4 times 2 minus cosine of 4x over 3 times 2x minus sine of 4x, all of that to the 2/3. Oh, oops, I'm sorry, I interpreted this top part wrong. I was reading this line incorrectly. Okay, so if I write this part out, this 4 only gets multiplied by the cosine of 4x. Sorry. So this will come out then as 2 minus 4 cosine of 4x. Okay, there's your final answer. Sorry about that. Okay, so for number 4. So for number 4, we have another chain rule type problem. And so once again, as we kind of look through this, the outermost function here would be this thing to the 7th. And then the next function in is all of this. And once again, so you'll notice that we have to use the chain rule here, but we're going to worry about that when we get to that. So let's just get started. So first things first, so I need to take the derivative of the outermost function. So I bring the 7 down. I leave all that stuff on the inside intact, and then I subtract 1 from the exponent here. Okay, and then I multiply that by the derivative of the inside function. Oops, and let me use my gold color just so you can kind of track the derivatives I'm taking. Okay, so now the thing is, when I take the derivative of this guy here, now I need to use the chain rule again. So I have to identify my outermost function. My outermost function in this case would be tangent, and my innermost function would be this x to the 4th. So now, as I prep to take this, the derivative of tangent is secant squared, and I leave the inside function intact, and then I multiply that by the derivative of the inside function. The derivative of x to the 4th is 4x cubed. Okay, so that was just taking the derivative of this guy here, and then we're still not done, right? I still have to take the derivative of this 3x. So it'll be that plus 3, okay? And so now it's just a matter of cleaning this up and making this look nicer. So let's go ahead and let's see. So this will be 7. Why don't we write this as 4x cubed secant squared x to the 4th plus 3. And then we have this other thing to the 6th power. And so there you go. All right, so for number 5, now I have to use the quotient rule here, and then as I'm using the quotient rule, I'm also going to have to use the chain rule, but we'll cross that bridge when we get there. I think the only thing that I want to state here is that the cosine squared x, so that is equal to cosine x squared, so we're going to need to remember that when we take the chain rule. Okay, so let's just jump right into this. So remember, we're going to be using the quotient rule for all of this, and first we take the derivative of the top function. So this is where we have to use the chain rule, and that's where thinking of this function in this format might be helpful, because I will have the outermost function, which is this thing that's being squared, and then I have this inner function, which is this cosine x. So if I take the derivative of the outermost function, I bring that 2 down, I leave the inside function intact, I don't worry about it, okay, And then I multiply that by the derivative of the inside function. So the derivative of this cosine function here is negative sine x. And so now I've taken the derivative of this whole guy, so I'm done with that first part. So I take the derivative of the top function, and then I multiply that by the bottom function. So I still need to multiply that by tangent x minus 3x. Okay, so that's just the first part, right? So now I leave the top function alone, so I write out cosine squared x, and now I take the derivative of the bottom function. So the derivative of the bottom function will be secant squared x minus 3. And then all of that gets divided by tangent x minus 3x. I square the bottom. Now, as far as simplifying this goes, I don't think there's like a whole lot more you can do to simplify this. So you can either leave this as like a giant fraction where, you know, you can at least bring this negative like out in front, but there's not a ton you can really do to simplify this. I will show you one way that you can simplify this. I usually look up my answers and compare them against a derivative calculator. So I'll just show you what this one derivative calculator showed me as a simplification, but there's not always like an agreed upon way to like do the final simplification. All right, so if I wanted to break this up into pieces, I guess what I could do is this would be negative 2 cosine x sine x tangent x minus 3x. So this would go over that denominator of tangent x minus 3x squared, and then I've got cosine squared x secant squared x minus 3 over tangent x minus 3x and then squared. Okay, so now you can see, oops, and I probably should have put some parentheses around this. So now you can see I can cancel out this with 1 power of this tangent x minus 3x. So that's like maybe the only other simplification you could really do. So if I wanted to show you the final answer, let me clear some space. All right, so final answer, so negative 2 cosine x, let's see, sine x, tangent x minus 3x, and then this minus cosine squared x, secant squared x minus 3 over the other stuff. Okay, there we go. Okay, so there's your other way you could simplify that. Okay, so for number 6, so this is going to require the chain rule. And I always like to point this out because I think this is one that kind of messes with people's heads a little bit. This is the inverse sine function. So just FYI, inverse sine x is the same as arc sine. Those are the two ways you can see it. So when you see this negative 1, it does not refer to an exponent. It is literally referring to the derivative of arc sine or the inverse sine. So not all calc classes will necessarily learn these. In the one that I teach, we do this, so that's why it's included in this video. But just in case you need a quick reference as to the derivative. Okay, so here's just a quick reference of your inverse derivatives. So you can pause the video here if you want to write them down or review them or whatever. Okay, so for our purposes then, I need the chain rule. So my outermost function is this inverse sine function. The next function in would be this square root function. And then the innermost function is going to be this 1 minus x squared. So now we can move on to party time here and start taking the derivative. Okay, so in taking the derivative of the outermost function, so this inverse sine, so I'm going to write this as 1 over the square root of 1 minus, now normally this would be x squared. However, in this case, I just square the whole inside function, right? So this will be the square root of 1 minus x squared squared, like that, okay? Okay, and then I continue on by taking the derivative of the next function. So the derivative of the square root function, this will be 1/2. I leave the inside function intact, and subtract 1 from the exponent. And then finally, I multiply that by the derivative of the innermost function, so that'll be negative 2x. And so there are all my pieces. Okay, so to clean this up now, let's see. So on top, looks like, let's see, the 2's will cancel out. So it looks like on top I just have, what is it, negative x. And then in the bottom, so let's see, I'm going to have this square root of 1 minus x squared, and then this square root of 1 minus, and then this will really just be 1 minus x squared. Okay, so this is going to be actually a little clever, if you will. There's a little bit of a hidden trick in here with this simplification. So let me make a little more space. And okay, so you're probably thinking to yourself, oh, I can simplify this part in here. And okay, so that is correct. So this becomes the square root of 1 minus x squared. And this, now I'm just going to have negative, the square root of negative x squared. Now here's where the cleverness comes in. So the first thing I want to do is I want to just think about this part here. So you can break up something like a square root. So let's say I have the negative x squared, square root of negative x squared. So I could break this up into the square root of negative 1 times the square root of x squared. Okay, now here's a property that I would kind of bet probably a lot of people kind of forget. So when you take the square root of x squared, so the thing about this is, since this is a square root, you need to like guarantee that this solution comes up positive. So you might think, oh, this is just x. This is not actually just x. You want to make sure that it is forced to be a positive answer. So the answer to this would actually be the absolute value of x, okay? So that's one thing. Now, in breaking this up like this, so what this is going to allow us to do is it's going to allow us to multiply this leftover negative 1. It's not going to be I, we're actually going to multiply it into this other square root over here. So let me kind of show you where we're at right now. So I've got this negative x, I've got the absolute value of x, which I just showed you. I still have this square root of negative 1, and then I have this 1 minus x squared. So now what I want to do is I want to multiply this square root of negative 1. I can just multiply this directly into these terms here. So what will happen then as I multiply this in is this will become negative 1, right, plus x squared. So just to finish this out then, the final answer, like truly simplified, this becomes the square root of x, and this will be x squared minus 1. So there's your actual final answer. So a little tricky with some of the simplification. So for number 7s, we're going to have to use a chain rule here. And once again, I pointed this out in the last problem, but I'll point this out one more time. This is not a negative 1 exponent. This is referring to the inverse tangent function. So if you forgot the derivatives to that, not all calc classes cover them. I cover them in mine, but I'll just quickly kind of flash those sets of derivatives for you so you can pause and write them down if you want. Okay. So to take the derivative of this, we've got to use the chain rule. The outermost function is the natural log, and then the innermost function is this tangent of x. So to take the derivative, I start with the derivative of the outermost function. So the derivative of natural log would normally be 1 over x, but now what I'm going to write instead is 1 over the inside function. Okay, and then I multiply that by the derivative of the inside function, and that derivative is 1 over 1 plus x squared. And that one's actually, this is a pretty quick derivative. The trick here, I think, was really knowing the inverse tangent. So let's see if I write this all down. Okay, I've got 1 plus x squared, so there's your derivative. Okay, so for number 8, this one is definitely implicit differentiation, you know, just by looking at it, because you've got, this function is not in terms of just x's, right? You've got x's and y's, they're all kind of hanging out with one another. So you know you're going to have to use implicit differentiation. So even if you're not told to use implicit differentiation, you know that that's the only way you can take this derivative if you have all your x's and y's mixed together like this. Okay, so now let's go ahead and work on taking the derivative. So I'm just going to start from the left to the right. Derivative of x squared is 2x. Okay, so now as we move on to this next part, now I have to think about the product rule here. So the way I'm going to think about the product rule, this root 5x, that is my first function, and then my second function is this this y, okay? So that'll just help me to kind of work through the product rule. Okay, so I'm also going to just set up these parentheses so that I remember to distribute this minus sign. Okay, so the derivative of square root of 5 times x is just going to be the square root of 5, and I multiply that by y. And then for the next one, I have the square root of 5x. I leave that alone, and I take the derivative of y. However, since it's implicit differentiation, when you take the derivative of y, you also have to include dy, dx, or y prime, whatever you want to do. Okay, so there's that part. And then I take the derivative of 3y squared, which is 6y. And once again, since I took the derivative of y, I write dy dx, and then all of this is going to equal 0 because the derivative of a constant is 0. Okay, so now, just so that I don't forget, let me just distribute that minus sign. Let me just distribute that. And then we can move on to the next phase of this, which is solving for dy dx. So anything that doesn't have a dy dx, i.e. these two terms here, we're going to send them to the other side. So let me do that. So I've got, let's see, negative square root of 5x dy dx plus 6y dy dx. This is going to equal negative 2x plus square root of 5y. And then I can factor out these dy dx's. So now I've got dy dx times the negative square root of 5x plus 6y, and then negative 2x plus square root of 5y. Let me just erase all that. Okay, and so now we're in the home stretch here. So I'll clear a little bit of space here. Okay, so now I can just divide out this part here, the part I don't want, to solve for dy dx. So I have dy dx, this is going to equal negative 2x plus the square root of 5y over negative square root of 5x plus 6y. And we're done. So number 9, we've got 2 plus x times inverse sine of 3x. Just a reminder, this is the inverse function, so this is not an exponent. This is referring to the inverse sine function. If you want to see a list of the derivatives for the inverse trig functions, here's the first list. You can pause if you want, and then here's the second list, and you can pause if you want. I have a whole video where I break down why these derivatives are what they are. You can check that out if you want. So for this particular problem, we have a couple different ways I guess we could do this. We could distribute this to this inverse sine function, or if we wanted to, we could also just use the product rule. Personally, I think that the product rule in this case will probably be the faster, easier way to go. So this will be my first function, and this will be my second function. Now, what you'll notice here is we have to use the chain rule here, but we'll worry about that when we get to that. So using the product rule, so the derivative of my first function is just 1, right? So the 2 goes away and the derivative of x just 1. So actually the first part of the derivative, multiplying 1 by sine inverse 3x, is just going to leave me with just that, right? Sine inverse 3x. And then for the next part of this, I leave the 2 plus x alone, and now I need to take the derivative of this guy. Okay, so to do that, what I need to do now is I need to think about the chain rule. So the outermost function is really this inverse sine function, and then the innermost function is this 3x. So first I take the derivative of the outermost function, which is going to be, let's see, 1 over the square root of 1 minus 3x squared. So normally this would be like x squared, but now we just take the inside and square it. And now I multiply this by the derivative of that inside function, which is just 3. So I multiply that by 3. Okay, so now I've got the inverse function, the derivative. It's going to be inverse sine 3x plus, and then we have some options of how to actually work this out, I guess, but I'll write this as 3 times 2 plus x over the square root of 1 minus 9x squared. And that's good enough for this one. Now, number 10 is pretty tricky, I think. You really have to kind of be on your toes for this one. So you'll notice that you've got x and y on like within each side of the problem, right? So you're probably gonna have to use implicit differentiation. But the issue here is that, so think about what derivative rules we have. We have derivative rules for like x to the n, right? So if I wanted to take the derivative of this, where n is an integer, I would just use the power rule. So I would do that. And then we also have derivative rules for like a to the x, right? So this would just be a to the x times the natural log of a. But we don't have anything where it's like x to the x. So we don't have anything like x to the x. So this is kind of a problem. I know that this is y to the x and x to the y, but it's kind of the same idea. So we don't have this particular derivative here, okay? So what that means then is we're going to have to pull out the big guns, if you will, and we're going to use logarithmic differentiation to solve this, because then at least we can get rid of these exponents. So that's the only way you can really solve this particular, or find this particular derivative. So what I'm going to do is I'm going to take the natural log of each side, and in doing that, that's going to allow me to bring each exponent down in front to get x times the natural log of y equals y times the natural log of x. And now from here, I can go ahead and take the derivative of each side using implicit differentiation. And I will use the product rule. So I've got x times the natural log of y. So on the left side, this will be the natural log of y plus x over y dy dx. So that's using the product rule. And this is my first function. This is my second function. And so now if I go to the other side, so now if I take the derivative of y, that's just 1. So I'm going to be able to natural log of x dy dx, because I just took the derivative with respect to y. And then for the next part, I'm going to have y over x. So there are kind of all my pieces. And so now what I want to do is I want to put these dy dx terms together on one side. And then I want to put these other terms that don't have the dy dx, I want to put those together on another side. Okay, so I'm going to have now x over y dy dx minus the natural log of x dy dx, and this is going to equal y over x minus the natural log of y. All right, so let me make some space. And now I can factor the dy dx out. So I've got x over y minus the natural log of x, and then this is y over x minus the natural log of y. So then in the end, my final answer will be y over x minus the natural log of y over x over y minus the natural log of x. This might not be the answer that you see, so what I want to do now is I want to clear a little space and just show you like one other way that you could simplify this. So let me clear some space. Okay, so the name of the game now is just to get rid of the fractions here. So what I'm going to do is I'm going to multiply by the common denominator between these two fractions, which would be xy. So I'm going to multiply the top and the bottom. I'm just going to multiply both of these by xy. So think about what happens then as you distribute that xy. So as I work through this, I'm going to have y over x times xy. So the x's will drop out, and I'm left with y squared. And then this will be minus xy times the natural log of y. And then in the denominator, oops, sorry, I should put that in the white color. So y squared minus xy times the natural log of y. And then in the denominator, that'll be x squared minus xy times the natural log of x. So that's another way that you could simplify those if you wanted. And then just one other thing I want to point out, so the order that you subtract and subtract things in will also kind of matter. So an equivalent answer to this, you could have everything flip-flopped. So I could also have xy times the natural log of y minus y squared over xy times the natural log of x minus x squared. Those are equivalent answers, and that just comes down to a factor, or it's a product of how you did your subtraction in some of those initial steps. Okay, so for number 11, I've got y squared equals x over x plus 1. So this is going to use implicit differentiation. And you can tell because this is y squared and not just plain old y. If this were plain old y, this would be a bit simpler. So, okay, we're going to go ahead and take the derivative of the left side, which will be 2y. Since I took the derivative of y, I'm going to write y prime here. You could also write dy dx. I'm just kind of switching it up. And then on the other side, so now I just need to use the quotient rule. So the derivative of the top function is just 1, and then I multiply that by the bottom function. And then I leave the top function alone, and I multiply that by the derivative of the bottom function. And then I just take the bottom function and I square it like this. And so now I've got 2y, y prime. Let's see, if I simplify all of this, this will just be just 1. And then still over that x plus 1 squared. So now to finish solving for y prime, I can just divide out the 2y. So this becomes y prime equals 1 over 2y times x plus 1 squared, and you're done. Okay, so for number 12 here, so I've got y squared equals 2e to the negative 1 over x. So this one, once again, is using implicit differentiation because this is y squared and not just y. So I can go ahead and start taking the derivatives of everything. So this is going to be 2y times y prime. And then on this side, so I might want to just take a second to think about what is this. So I could alternatively think about this as 2e to the negative x to the negative 1. So that might just help me. And now I can more easily take the derivative here. So I'm going to have to use the chain rule here. So the outermost function is the e, and the innermost function is this negative x to the negative first. Okay, so this will end up becoming, okay, so let's see, taking the derivative of the outermost function e would just be e, so I leave e, and then I've got negative x to the negative first, so I leave that alone. And then I multiply that by the derivative of the inside function, which would be, let's see, x to the negative second. That's what that would come out to be. Okay, so now I've got to simplify some of this. So I've got 2y times y prime equals 2e. I'll rewrite this as negative 1 over x. And then I guess I could write this over x squared. So now from here, you can see you've got, you can divide out the 2's on each side. So I can go ahead and cross these out. And then all I have to do is divide by this y here. So my final answer will be y prime equals e to the negative 1 over x over yx squared. And that would be the answer. So for number 13, I've got 1 minus x cubed e to the inverse secant of x. So once again, as a reminder, this is not an exponent, this is inverse secant. So that's its own list of derivatives. I'll just flash those up on the screen real quick. So here's the first list, you can pause if you want. And here's the second list, again, you can pause if you want. So, okay, so what we're gonna have to do then is we have to make some decisions, I guess, of how we wanna work with this. So we could distribute this, or we could just use the product rule. Personally, I'm gonna suggest that we use the product rule. So in this case, this is going to be my first function, and this is going to be my second function. Now notice here we're going to have to use the chain rule, and we will work on that when we get to that point. Okay, so I'm going to have f prime of x. So let's see, first I have to take the derivative of the first function, so that'll be negative 3x squared, and I leave the second function alone, so I can just rewrite this like that. Okay, so next I leave the first function alone, and now I have to work through the chain rule of this function here. Now, the outermost function here is the e function, and the innermost function is this inverse secant. So the derivative of e to the x is just e to the x, so I can write down e and then leave the inside function intact. And then I can just multiply that by the derivative of inverse secant. And that is 1 over the absolute value of the square root of x squared minus 1. And so from here, now we just have to kind of clean this up a little bit. So this will come out to f prime of x equals negative 3x squared e to the inverse secant of x plus 1 minus x cubed e inverse secant of x over the absolute value of x times the square root of x squared minus 1. And in this case, there's not really much more simplification you can do. Okay, so moving on to 14 here. So I've got y equals the natural log of x to the x. So I was talking about this type of problem in an earlier problem. So just to review, these are the derivative rules that we have. And basically what you're looking at here, this is kind of like something of the form x to the x. So I can take x to a number, or I can take a number to the x power, but I can't take x to the x. We do not have a derivative rule for that. So the only way to work through finding the derivative for this particular problem is to use logarithmic differentiation. So let me clear some space. And let's get the party started. So first things first, I need to take the natural log of each side. So I take the natural log of x. I know it looks a little goofy, but the thing that allows us to do that makes this problem much more approachable is now I can bring this exponent down, and from here I'm going to use logarithmic differentiation to kind of finish this. So okay, so on the left side now I'm going to take the derivative of the natural log of y, which becomes 1 over y, and then I'll write dy dx because this is logarithmic differentiation. And then on this side, I need to use the product rule. So first I take the derivative of this, just x, and so that's going to be 1, and then I multiply that by the second function, this natural log of the natural log of x, okay? And then I leave the first function, x alone, and now I multiply that by the derivative of this whole guy. Now, this one's going to require the chain rule, and just to be nice and clear with this, your outermost function is the natural log, and then your innermost function is this natural log of x. So if I take the derivative of the outermost function, that's going to give me 1 over the natural log of x. And then I multiply that by the derivative of the innermost function, which is just going to be 1 over x. And so now we can work on some simplification here. So I've got these x's are going to cancel out, and there's not really that much more that we can do. So I'm going to write out kind of where we're at. And there's like one other thing that you have to do with this that I think a lot of people kind of naturally forget. So let's see, let me write this out. Okay, so the thing about logarithmic differentiation is that you are really still just trying to solve for dy dx, okay? So don't forget that part. So you can see then you're going to have to multiply by y. So let me clear a little space. And so now I'm going to have that dy dx, this just equals y times all this other stuff. But here's the tricky part that I think a lot of people forget. So oftentimes when you use logarithmic differentiation, and it's a very specific thing that you're thinking about here. It's when you use it in this case. This is y equals a function. But it just so happens in this case that for this particular function, the reason we use logarithmic differentiation was we really had no other rules that we could like throw at this, right? So because this was y equals this straight up function, the idea here then is that you want to take this and you actually want to use that to replace it into y. So our original function was in terms of entirely x, and it would be kind of awkward in this particular case to suddenly have a y pop up in here. So we can easily substitute this y back for the original function. So that's really what we want to do. So that's something that I think a lot of students forget, and it's really just the context. So that's why we have to do it in this particular case. So notice I just replaced that function, and then I can just write the rest of this out, and now we're done. Okay, so for number 15 here, so I've got 1/5 x times e to the 5x minus 1 over 25 times e to the 5x. Okay, so in this case, what we're going to do here is we've got some power rule, and we've got some chain rule, and we've got some product rule. So let's just get right into it. So if I go ahead and take the derivative, so for this first function here, what I need to do is use the product rule. So I have 1/5 x as my first function and e to the 5x as my second function. So taking the derivative of x, that's just going to leave me with 1/5, and I multiply that by the other function. And then I have 1/5 x, and I multiply that by the derivative of this function. Now for this one, we have to use a chain rule. The outermost function is e, and the innermost function is to the 5x. So this will be e to the 5x times the innermost function, which is 5. So there are all the pieces for that one. So we've taken the derivative of this guy here, and now we move on to taking the derivative here. Now here we're going to have to use the chain rule again. Again, this is my outside function, this is my innermost function. So this will be minus 1 over 25 e to the 5x times 5. Okay, so now we've got some things that we can kind of simplify here. So let's see, I've got 1/5 e to the 5x. These 5's in the next part drop out, so this is xe to the 5x, and then this will simplify to 1/5 e to the 5x. And now I can see that these 1/5 e to the 5x's drop out, so this will just leave me with the answer xe to the 5x, and that's it. Okay, so for our last derivative problem here, so this one I made a little bit tricky. So I've got the natural log of the square root of this whole monstrosity here. So here's the thing. This was set up to make it very hard to take the derivative as is. But if you think about your properties of logarithms, this is going to come in handy, like big time here. So, okay, let's go ahead and set this up. So I'm going to actually rewrite my function y using all the properties I know of the natural log. So one thing to keep in mind here, so I could really rewrite this as x plus 4 to the 7th over x minus 5 to the 8th, all of that to the 1/2. So the first thing I'm going to do is bring that 1/2 power down. So this becomes 1/2 times the natural log of x plus 4 to the 7th over x minus 5 to the 8th. Okay, so in doing this, now what I can do is I can break this up using the quotient rule. So I can take this a step farther. So this becomes 1/2 times the natural log of x plus 4 to the 7th minus the natural log of x minus 5 to the 8th. And then that will allow me to take these exponents down, and then I can also multiply them by this 1/2 in front here. So this whole function now, I've rewritten it as 7 over 2 times the natural log of x plus 4 minus 4, because 8 divided by 2 is 4, times the natural log of x minus 5. Okay, so here's the deal. I would much rather take the derivative of this and just use the chain rule a couple times than having to deal with this whole crazy monstrosity here, because you're going to involve quotient rule and you've got chain rule, and this whole thing's just kind of a pain. But now I've rewritten this just using properties of logarithms to make it easier. So you can totally do that. So now let's clear some space. And now let's take the derivative of this much nicer function. So taking the derivative of this is going to be 7/2 times 1 over x plus 4. And the derivative of this inside function is just 1, so I'm just going to leave it like this. This is it. And then for this other part, this will be minus 4 times, let's see, times 1 over x minus 5. And again, the derivative of the inside function when I use the chain rule here is just 1, so I can just leave this as is. So my final answer then actually is something pretty simple here. 7 over 2 times x plus 4 minus 4 over x minus 5. And if you want to go a step farther with this, you can. So if you want, you can get a common denominator here. So I think a lot of this now just comes down to like preferences. In my mind, this is simplified enough, but again, I ran this through a derivative calculator just to see like how another website would simplify it. And they got a common denominator, so I'll just quickly walk you through the work for that now. So let me pause here and clear some space. Okay, and so now it's common denominator time. So what I want to do here, I'm going to multiply this by x minus 5 and x minus 5. And then for this other fraction, I will multiply this by 2 times x plus 4. So all of this 2 times, let's see, 2 times x plus 4. So now, let's see, the top will be 7x minus 35, and then let's see, I'll have this minus, let's see, what does this come out to? 8x plus 32. Now, notice that I'm subtracting off this fraction. So I put this numerator work, I put it in parentheses, and then I subtracted it off to make sure I captured the minus sign that applies to this whole fraction. And all of this now is over the common denominator, 2 times x plus 4 times x minus 5. And so now, let's see, what am I left with? This becomes negative x minus 67 over that whole denominator. So that's another way you could simplify just a little bit farther if you wanted to. Okay, so this problem, find the normals to the curve 4x minus y plus xy equals 0 that are parallel to 4x plus y equals 0. This is a pretty tough problem, I think. So this is going to take us a few minutes to solve. So first of all, we're being asked to find normals to this curve. So we need to implicitly differentiate this, but we need those normals to be parallel to this line here. And just looking at this, I don't know what the slope is. So what I want to do first is I just want to think about what slope is it that I need. So I have 4x plus y equals 0. So if I put this into slope-intercept form, this will be y equals negative 4x, and now I can see that the slope here is negative 4. So this needs to be the slope of my normal line, okay? But when we take the derivative of this, we're actually going to find the tangent line. So what makes a normal line, how are a normal line and a tangent line related? So this is the opposite reciprocal of the slope of the tangent line. So for the tangent line, the slope that I would need is positive 1 over 4 because that would be my opposite reciprocal. So this is the slope that I want to get to then for this particular derivative, if that makes sense. Okay, so I wanted to just note that. So let me clear a little space. And now let's focus on taking the derivative of this curve. So I have to implicitly differentiate because this is in terms of x and y. So the derivative will be 4 minus dy dx, because the derivative of y will just be 1, and then when you take the derivatives of y, you write dy dx. And now here I have to use the product rule. So when I take the derivative, this will be plus y plus x dy dx, and then this will all equal 0. So first thing I need to do now is solve for dy dx. So I'm going to put these two terms onto the other side, and then I will group together the terms that have dy dx in them. So let's see. So I've got, how about x dy dx minus 1 dy dx. This will equal negative 4 minus y. And so now I can factor out the dy dx, and then I can finish solving this to get that dy dx will be negative 4 minus y over x minus 1. Okay, so here is, this tells me how to get to the slope of a tangent line at a particular point. Now, the tricky thing here is we don't have any of these points, right? So this is where this is going to get kind of tough. So this is really the information that I need here, and now what I want to do is kind of back up and make some space, and then we're going to think about this a little more deeply. Alrighty, so now I've got my, this is the slope that I want, and this is how I would find the slope at a point. So what I want to do to start is I want to set these two things equal to one another. So I've got negative 4 minus y over x minus 1. I want this to equal 1/4. Okay, now here's the thing. We're looking for a point, and you can tell just by looking at this, right? We're not going to find that point, right? Because we have x and we have y. Now, if we just had one of those variables, we'd be able to find the point and it'd be all happy and we'd be good. But we can already tell we're not going to be able to find the point. So now what we have to do is get a little more creative. And this, we want to think of this more as a constraint, meaning this is kind of giving us some idea of how the relationship between the x and the y should be. But now I need to relate this to another equation, namely this one here, because between these two, these are really giving me the structure of how my x and y's should relate to one another, okay? So this is in terms of x and y, this is in terms of x and y. Now, if I solved this in terms of one of those variables, then I could relate it to this equation. So it's really just a system. So what I'm going to do is I'm going to multiply the 4 over to this side. So I'll multiply the 4 here. And then I'll also multiply this side by the x minus 1 so that I can get rid of this denominator and this denominator, okay? So what I'm left with then is this, let's see, and this 4 will cancel out, and this x plus 1 will cancel out. Okay, so I'm left with 4 times negative 4 minus y. This is going to equal x minus 1. And so now you can see we can at least easily solve for x in this case, which will then allow us to substitute back into this equation. So we've got to be patient here. We're kind of on a journey. So if I continue this is going to be, I'm going to distribute that negative 4, or that 4, so this becomes negative 16 minus 4y, this equals x minus 1. So then ultimately I get that x will equal negative 4y minus 15. Okay, so this is now telling me one part of the relationship between the x and the y's, and I'm now going to substitute this result into this equation. So let me clear some space. Now we'll take this condition and we're going to plug it just straight into this. So I've got 4, and where it was an x, now it will be negative 4y minus 15 minus y plus negative 4y minus 15 times y. This needs to equal 0. So now I need to go through and distribute everything and kind of clean this up. So this becomes negative 16y minus 60 minus y minus 4y squared minus 15y equals 0. So let's continue on with this. So this will give me negative 4y squared, let's see, minus 32y minus 60 equals 0. Now this looks factorable. So if I factor out the negative 4, I get y squared plus 8y plus 15 equals 0. And that totes my goats factors. Hooray. Okay. So that guy factors, and this is helpful because this is now going to give us a point, and once we have a point, we know what slope we need, and you need a point and a slope to figure out what this normal line is going to be. So I have then in this case y needs to equal negative 3 or y needs to equal negative 5. But wait, there's more. So remember now, this was in the constraint of the system that we created, just to make this nice and clear. We made it off of this equation and off of this equation. So using one of these two equations now, I now need to figure out what my y's are. So let's see. Why don't I, I'll just plug it back into this equation. So I need a little more space. So let me clear some room. Okay. So let's plug y equals negative 3 into this equation. So I get 4x minus negative 3 plus negative 3x. This needs to equal 0. So let's see, this gives me x plus 3 equals 0 when all is said and done. So this means that x would equal negative 3. So I'll note that here. X equals negative 3. There's one pair. Now for the other one, using y equals negative 5, I'll plug that in again. 4x minus negative 5 plus negative 5y equals 0. Okay, oops, sorry, negative 5x. Okay, so now this gives me negative x plus 5 equals 0. So if I work this out, then I will get that x equals positive 5. So the other pair here will be x equals positive 5. So now I have two pairs of points. Now, you might have forgotten what was the point of this question. So we are trying to find the normal line to this curve that has our desired slope, and the tangent line has the slope of 1/4, so our normal line will have the slope of negative 4. So now, let me just maybe note that, let's see, we need m equal to negative 4. Okay, so great news. So now we have everything that we need to really do this problem. We have a point, we actually have 2 points, and we have a slope. So what I'm going to do is I have to find now two normal lines. It did say normals, right? So that indicates more than one line. So let me clear some space. All right, so I'm going to use my good old point slope form, like so. So let's see, using the first point, this will become y plus 3 equals negative 4 times x plus 3. So I plugged in this point and then the slope into my point slope form. And so from here, now I'm going to have y plus 3 equals negative 4x minus 12. So this becomes y equals negative 4x minus 15. There's one normal. And then for my other normal, I'm going to have y plus 5 equals negative 4 times x minus 5. So now I've plugged in this point into my point slope form. So if I simplify this, I get y plus 5 equals negative 4x plus 20. So then this becomes y equals negative 4x plus 15. And so here are my two normals. So that was the actual answer to the question. So that was definitely a tough one. Now, number 18 is definitely a tricky question. So let's take a look at this. So find an equation for a line that is tangent to the curve y equals x squared plus 3x plus 1 that goes through negative 1, negative 10. Okay, so this question is one of those questions where if you were struggling with it, I think that's fine. It's a hard question. And there are a couple parts of this where you really have to sit with this. So I would encourage you just to consider, if you hear an idea as I go through this explanation and then you think you might see what the solution is, consider pausing the video and seeing if you can get to the rest of the answer. So this question is really best, it's very good for you to have problems where you don't immediately know how to solve them and you have to struggle with them. The more you struggle and you sit with that struggle and you don't panic, you just kind of sit with it, the better you're going to get at overall problem solving. And it's just a real skill that it really does take practice and patience. Now, what I want to talk about is what is this situation? So, okay, I have in this red graph here, so this is my x squared plus 3x plus 1. So here's that. And then this negative 1, negative 10, so I've marked that down here on this graph. And so what it is that we're trying to do, this point is not even on this graph, right? So what we're trying to do is we're actually trying to find what point that is tangent to this would go through this point here. And so just to bring this visual a little bit more clear, so here's some point. I don't know what this point is, so we got to figure that out. What is this point that would allow me to then go through that point? So this is going to take some definite work. Now, like I said, we don't know what that point is, so I'm going to give you a couple of hints here before we get too far into this. I'm just going to call this point xy for now. We will figure this out as we go along. We will determine what this point is. And remember that tangent is related to slopes, and the slope of a line between 2 points, there's another way that you can calculate that from algebra. So all of that is meant to be a little bit of a hint, so if you want to pause and play around with this a little bit. Again, I think that's one of the best things you can do for yourself. Okay, so we know we see tangent is in this, so I know I'm gonna have to take a derivative, so I'll just get that out of the way. So this becomes 2x plus 3. Okay, and okay, this represents the slope at a point on this graph, but I don't know what point I want from this graph. That's kind of the issue. So the next thing that I could do is I could try to figure out what is that slope that I want. And while I can't figure out that exact slope, I can kind of figure out the structure of it, because I have technically 2 points. Even if one of these is not fully filled in, I can take this at least a step farther. So what I can do is I can use the slope equation for those 2 points. And so this will become then y minus negative 10 over x minus negative 1. Okay, now I don't know what xy is, but the one thing that I do know is if I knew that what this point was, I would want this to be equal to this. These two things have to be equal to one another. So let's just go ahead and set them equal to one another. So, all right. Now that I've set these equal to one another, I think that you can see there's like one ideal thing we might be able to do with this. It would be nice if we could solve for x. Now there's a problem. I can't solve for x in this because I've got this y here. So what can I say about this y point? So remember, this y point corresponds to this graph here, right? So what can I say about the structure of this y point? Well, I actually know how y relates with the x's. It's from this equation here. Okay, so what I can do then is I can replace this y equation with you know, the original, you know, equation of the line that we had. So this will be 2x plus 3 equals x squared plus 3x plus 1. So this is the y part of this, and then we still have this plus 10. So we've got this plus 10 over x plus 1. And now this I feel pretty confident that I could solve for x for this. So let's make some space. Okay, so to solve for x, so I need to multiply both sides by the x plus 1. So I've got 2x plus 3 equals x plus 1. And then on the other side, I'm going to go ahead and just collect my like terms. This becomes x squared plus 3x plus 11. And now I need to go through and multiply all this out, which if I multiply all that out, I will get 2x squared plus 5x plus 3. And now let's see if we can actually solve this. So I'm going to subtract all of this to the other side. So if I subtract this off, 2x squared minus x squared will be x squared. 5x minus 3x is 2x. And then 3 minus 11 is negative 8. Okay, and so now if I try to solve this, so I've got x, let's see, x plus 4 and x minus 2. So my two solutions here are x equals negative 4 and x equals 2. So I have two solutions. So now you might be thinking back to that picture that I showed you, and you might think, oh wait, but we only had the one tangent line that we looked at. So I just showed you how this is possible, but now I'm going to show you like the real picture. So here we found this blue line, so this is where x is 2, but it turns out there's actually a second point that goes through negative 110. So we found the other tangent line, and so this is what that situation would look like. So yeah, it's totally possible that we could have 2. Okay, but we are not done. So remember, the actual set of directions here were to find the equation of the lines. So I have the x coordinates, and now I really need to go back to the beginning of this problem, I guess. So going back to the beginning, I wrote down the two x's that we just found. So using these x's, now we can find the equation of our tangent line. So first things first, I just need to figure out what are the y coordinates associated with these x's. So if I take y of negative 4, so let's see, that's going to give me 16 minus 12 plus 1. And so that'll be 5. So we have the point negative 4, 5. And then if I take y of 2, so that's going to give me 4 plus 6 plus 1. So let's see, that's going to give me the point 2, 11. Okay, so now I have those 2 points. And so remember, we use those points and we still have to find our slopes, right? So we need to get tangent lines here. So just a reminder, the derivative of this original equation was 2x plus 3. So now for each one of these situations, I can determine what the slope of these tangent lines would be. So let me just maybe mark up here, so negative 4, 5, and 2, 11. So that's the relevant information that we need, and let me clear some space. And now let's go after those tangent lines. So starting with the first point, so if I take y prime of negative 4, that's going to give me negative 8 plus 3, so that equals negative 5. So there's my first slope, so this is going to be my m. And so now I can use my point slope formula. So I needed a point and I needed a slope. So I found this point and this slope, so now I can go through kind of all the work. So this becomes y minus 5 equals negative 5 times x plus 4. So that's going to give me y minus 5 equals negative 5x minus 20. And so the equation of my line will be negative 5x plus 15. So there is one one of my lines. So let me just maybe mark that up here. Y equals negative 5x plus 15. And now I need to work on the equation for the other point. So let me clear some space. Okay, so now I can take a look at y prime of 2, so working through the second point. This is going to give me 4 plus 3, so this is going to be my slope of 7, so that will be my slope for my point slope equation. So plugging all my information in, I'll have y minus 11 equals 7 times x minus 2. So I get y minus 11 equals 7x minus 14. And so in the end, I will have y equals 7x minus 3. And so this is one line and this is the second line. So that was definitely a good, difficult problem. Okay, so for number 19, we need to find the 99th derivative of sine of x, which might sound intimidating, but you just want to think about like the derivatives of these trig functions first. So let's say that I'm starting with sine of x. So the first derivative is cosine of x. The second derivative is negative sine of x. The third derivative is negative cosine of x. And then the fourth derivative will get me back to sine of x. So there's really like a pattern here. And if you're nervous and you just want to kind of convince yourself of it some more, you could blow this pattern out just one more time so you can see, right, I just wrote it out here just in case you wanted to see it. So every time we go through like a cycle of 4 derivatives, right, we end up getting back to sine. So that's really what we need to think about then with this derivative here. So let me clear a little space. So let's just think about how many times do we go through a cycle of 4 with 99, and I can really just use like, you know, good old division for this. So if I were to set this up and I just do my division here, so let's see, this is going to go through a total of 24 times. So really we're going to go through the cycle 24 times total, and then in the last cycle we'll get up to that third derivative. We basically have now just figured out, so y to the 96, so this will be the fourth cycle. This gets us back to sine of x. So then the 97th derivative is going to be cosine of x. The 98th derivative will be negative sine of x, and so that would mean that the 99th derivative will be negative cosine of x. And so there's my answer. And again, that 96, so that's going through the 4 cycles. So when I get to, so remember we just did this division, so 4 times 24 is 96. So I know that the 96th cycle will be back to sine, and then we can just finish the cycle that way. So for number 20, we have to find the second derivative of this function x squared times x to the 4th minus 1 to the 6th. So I'll tell you that I think the hardest part of this is probably in the simplification, because you want to simplify the final answer. But let's just go ahead and get started with this, and we'll work through that as we get there. So we're going to have to use the product rule with this. So I've got x squared, and then I've got this whole function here. So taking the derivative of x squared, that's just going to be 2x, and then I multiply that, as we all know, by x to the 4th minus 1 to the 6th, so I don't do anything to that. And then I add to that x squared, and then I use the chain rule for this other part. So I'm going to multiply that by 6x to the 4th minus 1 to the 5th. And then I multiply that by the derivative of the inside function, which is 4x cubed. All right, so now we want to just try to simplify this as much as we can. So this will simplify as 2x times x to the 4th minus 1 to the 6th, and then plus, let's see, this will be 24x to the 5th times x to the 4th minus 1 to the 5th. Okay, so here now we can simplify this a step farther, and I want to get us kind of in that mindset of simplifying. So notice that among these terms, both of these have this x to the 4th minus 1. So I can factor out this x to the 4th minus 1 to the 5th. I can factor that out. So I'm going to go ahead and do that. So this becomes x to the 4th minus 1 to the 5th. So what am I left with then? So here, I still have that 2x, and then I still have one factor of this x to the fourth minus 1. And then for this other factor, I'm just left with 24x to the fifth. Okay, so let's simplify this piece as far as we can. So this will be x to the fourth minus 1 to the fifth, and then this is 2x to the fifth minus 2x plus 24x to the fifth. So in the end, I have x to the fourth minus 1 to the fifth times 26x to the fifth minus 2x. Okay, so there is my fully simplified first derivative. So I need to clear a bunch of space now so we can take the second derivative. Okay, so now let's work on the next derivative. And all right, so we're going to have to use the product rule again. This is my first derivative, or this is my first function. This is my second function. So taking the derivative of this part, so this becomes 5. I leave the inside function intact, subtract 1, and then multiply that by the derivative of the inside function, which will be 4x cubed. So there's that first part. And I multiply that by 26x to the fifth minus 2x. So remember, you take the derivative of this function, and then you multiply it by the second function. So I've got to bring that along for the ride. Okay, so that's the first part of this. So now I leave the first derivative alone. And now I take the derivative of the second part, so this will be 130x to the fourth minus 2. Okay, so now we've got quite a bit of simplification to do here. So let's see, this is going to be 20x cubed. I've got x to the fourth minus 1 to the fourth, and then 26x to the fifth minus 2x. That's the first part. And then the second part is still just this x to the fourth minus 1 to the fifth, and then 130x to the fourth minus 2. Okay, so now what I want to do is as I look across the landscape of this problem, I want to factor out this x to the fourth minus 1 to the fourth again and simplify from there. So the algebra is a little tricky here. Okay, so if I factor out this x to the fourth minus 1 from this first part, I'm left with 20x cubed times 26x to the fifth minus 2x. And then for this other part, this will be x to the fourth minus 1, and then 130x to the fourth minus 2. And okay, yeah, all of that. Whew, okay, so now let me clear a little space. Okay, so now I want to start multiplying kind of all of these parts together. So I've got y double prime, got this x to the fourth minus 1 to the fourth, and then let's see. This is 520 x to the eighth minus 40x to the fourth plus 130 x to the eighth minus 2x to the fourth minus 130x to the fourth plus 2. Oof, okay, so now I've got y double prime, so I've got this x to the fourth minus 1 to the fourth. So let's collect our like terms. So this becomes 650 x to the eighth minus 172 x to the fourth plus 2. Okay, now if you really wanted to go factor crazy here, we could technically factor 2 out of this. So let's see, let's just factor out 2. So then I'm left with 325x to the eighth minus 344x to the fourth. Oops, sorry. I meant to divide. 86 plus 1. Okay, so there is like a fully simplified answer. So it's kind of a lot of work from an algebra perspective. Okay, so for 21, we're being asked to find the second derivative of x cubed plus y cubed equals 125. So we have to use implicit differentiation here. So we can tell that too because there's x and y, they're in the same side. So first we start by just taking the first derivative. So I have 3x squared plus 3y squared dy dx equals 0. So to solve for this, I have, let's see, 3y squared dy dx equals negative 3x squared, and then I have dy dx, this is going to equal negative 3x squared over 3y squared, so this will be equal negative x squared over y squared. Okay, so there's my first derivative, so maybe I'll note that. So dy dx equals negative x squared y squared. Okay, so I need to clear some space. And now I'm going to take the derivative of this guy. So this is going to give me my d squared y dx squared. So I've got to use the quotient rule now. And you know what, let's add the negative up on top here. So the negative can go, you could move the negative, so I'm just going to move it up top so I don't forget about it. Okay, so now let's see, I'll take negative 2x times y squared, so using the quotient rule, minus, so now I leave negative x squared alone, and then I multiply that by the derivative of y squared, which is 2y. However, now I need to include dy dx. Now, if you haven't watched my videos on taking second derivatives with implicit differentiation, we're going to deal with this at a later time. So we're just going to keep plowing ahead with taking the derivative for a moment here. So then I divide all of this by y squared to the fourth. Okay, so now we can simplify this farther. So d squared y dx squared. So this is negative 2xy squared plus 2x squared y dy dx over y, oops, and I don't know why I wrote this to the fourth. This should be y squared, so this should go to the fourth power. Okay, sorry about that. All right, so we're just about done with this, but the one thing is, so in this second derivative, we cannot refer back to the first derivative. So now this has to be replaced with what our first derivative was. So let me make some space. And now, just to save space, so I'm going to replace this now with my dy dx. Okay, so I'm going to erase this, and I'm going to replace it with that dy dx. And so now you just finish whatever other simplification that you can really do. So I've got d squared y over dx squared. So now this is negative 2xy squared plus 2, and then this becomes x to the fourth. Oops, and this should be negative again, my bad. This now becomes negative again over y, and then all of that over y to the fourth. And if you wanted to simplify this a step farther, so you could multiply everything by y so that you get rid of this y in the denominator. So let's see, if I multiplied both the top and bottom by y, then I would get negative 2xy cubed minus 2x to the fourth over y to the fifth. So that would be one step farther you could take it. And this would be your second derivative. So for 22, so we have a word problem here in 3 parts. So I've got a 12-foot ladder is leaning against a house when its base starts to slide away. By the time the ladder is 10 feet from the house, the base is moving at the rate of 4 feet a second. So we have 3 very different questions related to this scenario. The first question is, how fast is the top of the ladder sliding down the wall? So if I just want to model this situation, so here's my ladder and the ground and the wall. So here's my wall, here's the ground. Okay, so reading this problem, so the thing I've talked about in some of my other problems is that you want to pick out in this scenario what is not changing. So I've got this 12-foot ladder. So when you look at these numbers, think about, are they constantly changing? So this 12-foot ladder, that's not going to change. It's going to be a 12-foot ladder no matter what. So this is 12 feet, and that's really a constant. So I'm just going to note that there for myself. So now this situation is talking about the time the ladder is 10 feet from the house. So this is talking about this distance here. So this is 10 feet. But think about this. The ladder is moving. So we're talking about a moment in time now. So this is a constant, but this is not. And so maybe I'll just note this is not constant, so I don't forget. So we're talking about that moment when it's 10 feet away. The base is moving at the rate of 4 feet a second. So I'll also note that this is moving, since it's not constant. It's moving at this rate of 4 feet a second. So the question is, how fast is the top of the ladder sliding down the wall? So you've got now really like 3 different quantities here. So you've got this, this, and this. How do you relate these 3 sides of this situation together? Well, you use the good old Pythagorean theorem, right? So that's going to be a squared plus b squared equals c squared. And okay, so now I have to kind of label my sides here. So I'm just going to note this side, you know what, we'll call this side A, we'll call this side B, and we'll call this side C. Now, if you remember how related rates work, after you figure out what that geometric situation is, you want to plug in the thing that's constant. So the things that aren't constant, this is changing, so I'm not going to plug this in for A. But this 12 is never going to change, so it's not going to have like some rate of change. So when we take the derivative of it, it is going to be 0. So I'm going to just restate this equation now for this situation to look like this. And 12 squared we know is 144, so I'll just plug this in as 144. Okay, so now I want to bring rates into this situation. So I take this physical situation here and I take the derivatives so that I can bring the rates in. And I want to differentiate with respect to time. So for this part, I get 2a, and then this becomes dA dt, so that's with respect to time, plus 2b, and this is dB dt. And then this will just equal 0, because like I said, the thing that's constant, it has no rate associated with it. The ladder is not changing at some rate. The ladder is just always 12. So now, let's see if I've got enough to kind of work with this. So I know that we are talking about being 10 feet away from the house. Let's see. Oh, I can also divide this whole equation by 2. So why don't I just rewrite this as, we'll get rid of these 2's. So for the A, I'm going to plug in the 10. And we know that this is sliding at a rate of 4 feet a second. Now we have some other issues here. What do I do with this B and this dB dt? Well, the question is, can I figure out what this B side is? So I know that this is 12, this side is 10 at this moment, so can I figure out what this side is? Yes, I can. I have to just go back to the Pythagorean theorem. So if I have, let's see, 10 squared plus B squared equals 12 squared, what I end up getting is that B squared is going to be equal to 44. So B is equal to the square root of 44. So there's my B if I go through and I actually solve for it. So that I can plug in for my B, and then the only thing I don't know is my dB dt, but hey look, that's exactly what we were trying to solve for. How fast is the top of the ladder sliding down? That's exactly what we're finding here. So I have 40 plus the square root of 44, dB dt equals 0. So then you just solve for dB dt, and you will get that this is negative 40 divided by the square root of 44. So this is good, right, that this is negative, because that's indicating the negative part of that indicates that it's moving downward. And so then this would be the rate of feet a second. So there's your answer. At what rate is the area of the triangle formed by the ladder, wall, and ground changing? So for this one, so once again, if I just draw the picture here, so this is the situation that we have. And so you can see this does form a triangle. And so once again, thinking about basically the same stuff that we were talking about in part A, the one side that doesn't change is this side. So this is our constant. This is the size of our ladder. The ladder is 12 feet no matter what. Now, the other thing that we got out of this is this 10 feet. So this is changing. And this is also moving at this moment at a rate of 4 feet a second. And then from our last problem, so now we know that this side is the length of the square root of 44. And this is going down at this rate of negative 44 over the square root of 44 feet a second. So all that was from the last one. So sorry if you're having a little trouble reading that. Actually, let me see if I can make this picture better. Okay, there's a better picture for you. All right, so now I need to think about area, right? So my area of a triangle is 1/2 base times height. So now if I think about all these pieces, my base is this part here, and my height is this part here. So what's interesting about this is that the 12 has no place now in this particular formula, right? So context really matters. So now that we've changed the formula of the situation, this totally changes the context. So both of these, the base and the height, are changing. So now as I take the derivative of this, so once again I'm going to take the derivative with respect to time. So this will be dA dt equals 1/2. So I have to use the product rule. So first I take the derivative of b, which will just leave me h, and then this is dB dt, and then this will be 1/2 b times dH dt. Okay, so there's all my pieces. So what's interesting is I needed all this information from part A, but the 12 actually doesn't have anything to do with this, and now I have enough information to solve this because I can just plug everything in. So I want to figure out how the area is changing, i.e. I want to figure out dA dt. So I know what the h is. The h was this square root of 44. My dB dt, that's this right here. So this is talking about the base. Then taking my 1/2 times the base, so that was 10, and multiplying that by my dH dt, that's this rate right here. So that's -40 over the square root of 44. So now those are all the pieces that would get me to my answer, and that comes out to be some decimal. So I'm not too worried about the decimal. Let's see. Actually, I guess I can simplify this a little bit more. So this will give me, let's see, I'll put this up here. dA dt, this becomes 2 times the square root of 44 minus 5. Let's see, actually 5 times 40 is 200 over the square root of 44. So there's all the pieces that would go into that, and then you can plug that into your calculator for the final decimal answer. At what rate is the angle between the ladder and the ground changing? Okay, so now thinking back to our situation, I've got my wall, I've got my ladder. So I'm interested in this angle here. So this is going to be my little theta. All right, so thinking now about kind of what we know, we're probably going to have to use all the information that we've gathered from the other two parts. So I will just go ahead and label this one more time. So this is 12 feet, this is 10 feet, and this is going this way at a rate of 4 feet a second. And then let me make a little space to finish the drawing. Okay, so I've got all my pieces here. So now I'm interested in this angle right here. And at what rate is the angle between the ladder and the ground changing? So now we have to think about what kind of equation would relate kind of these sides to my theta. Well, you're going to want to use one of our trig functions, so sine, cosine, or tangent. So let me just write those down for a moment so we have a visual. So we have these three kind of basic trig functions to choose from, and I wrote down just the sides just as a visual. So thinking about which one of these that we want to choose, so if I were to choose this first one, so starting with theta, I'd have opposite over the hypotenuse. So the benefit of choosing this particular equation is that at least I have one side that is constant, so I know when I take the derivative, I don't have to worry about messing with the side that's like one less letter in my like rates equation. But the downside with this is that I just don't like the numbers on this side. That's just really the only downside. So now thinking about cosine of theta, so adjacent over hypotenuse. So we're talking about this side over the hypotenuse. So this is going to be just 10 over 12, or well, actually this side is changing, so this will be a variable, but the 12 still stays constant. So that's good, that's happy. Now tangent of theta is going to be opposite over adjacent, so opposite over adjacent. The bummer with this is that both sides are changing, and I don't think we want that. We want to have, like, if we can put a constant into our equation, it makes taking the derivative easier. So after evaluating kind of our three options, I think this is our best option. So let me clear some space. And now we're going to set up our equation. So I have cosine of theta. So let's call this side x, So this will be my adjacent over my hypotenuse. So there's the situation. And so now if I want to figure out like my rates, I can pretty easily do this. So taking the derivative of the left side, this will be negative sine theta d theta dt, because remember you take all derivatives with respect to time. And then on the other side, this just becomes 1/12 dx dt. Okay, now I know the rate to put in here, so I can go ahead and plug in the 4. The one thing I don't know is this theta, and I also don't know the d theta dt. Now notice that the question is asking at what rate is the angle between the ladder and the ground changing. So this d theta dt is actually what we're looking for. So I need to be able to plug in something for this theta. And considering I know what's happening in this moment, I have this cosine of theta is 10/12. We're talking about a particular moment. I can just use cosine of theta equals 10/12. So to solve for theta, I just take the inverse cosine of 10/12. And that gives me this kind of funky decimal, but that's okay. So I'll just use 0.586. So this is my theta, so I can plug this now into the equations. This becomes negative sine of 0.586 d theta dt equals 1/12 times 4. So let me clear a little space. So then my d theta dt, this will be equal to, let's see, 1/3 times negative sine of 0.586, and this came out to negative 0.603. Now, taking a second just to think, does this actually make sense? So as the ladder starts to come down, this angle is going to get smaller and smaller. So the fact that this is a negative rate does indeed make sense. So this is going for radians a second as our unit. Okay, so for number 23, are there any points on the curve y equals x minus e to the negative x where the slope is -1? If so, find them. Okay, so for this one, I just want to give myself a little more space. So the first thing that we want to do is we want to take the derivative, of course. And so let's see, I take the derivative. The derivative of x is 1. Now remember, you have to use the chain rule for this next part. So this will be e to the negative x times the derivative of negative x, which is -1. So my derivative then becomes 1 plus e to the negative x. And what I'm interested in is, can this equal, or can this have a slope of -1? So I need to set my derivative equal to -1. And if I subtract off the 1, I get that this equals -2. And so then, maybe a better way to visualize this would be 1/e to the x. That's another way that you can write that. Can that equal -2? Is this possible? Is there any way that I could plug in an exponent to this to get a negative number? This is not possible. So in this case, there are no points. Okay guys, so if you made it to the end of the video, congratulations. This was definitely a tough problem set. I'm not gonna lie, this video took me a couple days to make. So thanks a lot for watching. Thank you for your support, and I'll catch you guys in another video.